out.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Thank
Go.
you to everyone who is attending this program through various live broadcast. This program is currently live broadcast by India Science TV, the OTT channel established by Department of Science and Technology and run by Vigyan Prasar for popularizing science through visual media. And also the same program is currently on air through various other social media, including Facebook and YouTube. Today, we are going to have the finale of the Ramanujam Yatra, a major program that was initiated and organized by Vigyan Prasad between April 2020 and December 2020. Ramanujam, the greatest mathematician produced by India, was born on December 22nd, 1887, and today is the 133rd birth anniversary. Further, unfortunately, he died young in 1920 on April 26. That makes this year as the 100th death anniversary. To pay homage to Ramanujam and to popularize mathematics, Ramanujam Yatra was conducted by Vigyan Prasad. And today's program is the grand finale of this Yatra. We are very happy and thankful to the co-organizers who have joined us in conducting today's program. International Center for Theoretical Sciences, TIFR, Bangalore, Pi Mathematics Association, Chennai, Ramanujan Mathematical Society, Geetham deemed to be University, Visakhapatnam, Hyderabad, Bangalore, Punjab Engineering College, Chandigarh, Punjab University, Chandigarh, and Kerala School of Mathematics, Trivandrum. And we are also thankful to the India Science for carrying this program live on air. Now, I would request our director, Dr. Nakul Parasar, to introduce the Ramanujam Yatra, and subsequently, Dr. R. Ramanujan of Institute of Mathematical Sciences would introduce the speaker, and then our speaker, Professor Manjul Bhargava, would deliver his lecture. And all the participants, you can post your comments and question on the chat box on the respective social media platform in which you are watching. We will be able to pick up those comments and questions, and then in the end, our speaker would address some of those questions. May I request our director, Dr. Nakul Parasar, to introduce Ramanujam Yatra and start this program.
Thank you, Dr. Venkateshwaran. Thank you so much for getting us to this point. In fact, much before I talk about the Ramanujam Yatra, I think it's important and very relevant to, first of all, thank Dr. T.V. Venkateswaran to have thought about this Yatra, organized it, and executed it so meticulously. We all met in January, a set of people who've been working relentlessly for past many years in the area of uh, propagating mathematics, making it understandable and very interesting to the masses. This is when we all sat together for a meeting, formed a core committee, and decided that April 26th, which happened to be the 100th year for the day when Ramanujam passed away. We all came together. We decided up until December 22nd, which is Ramanujan's birthday, as well as the National Mathematics Day. So may I also congratulate you and wish you a very happy National Mathematics Day. Uh, Ever since we got into this whole plan for organizing various functions from April 26th till December 22nd, we thought we'll have simultaneously two lectures every month. And in these two lectures every month, we decided one would be in an Indian language and one would be in English, which would, of course, be delivered by an expert who has been following Ramanujan from for quite some time. And in this course, I am indebted to Dr. Ramanujan of the Indian Institute of Mathematical Sciences for having worked very hard and gotten us all these yeah, all this while a number of speakers from different walks of mathematics. And in this course, we feel very honored, privileged, and very touched, moved, and inspired by Professor Manjul Bhargava to have accepted our invitation to deliver this lecture. Interestingly, in this whole period of April 26th up until December 22nd, where we had grand plans to organize monthly seminars, workshops, in person meetings. Uh, Due to COVID 19, we had to put them back and get into this virtual mode. I'm glad to share we were able to connect with a greater audience in different parts of the country in different languages, where different subject matter experts spoke about Ramanujan in their languages. I'm also happy to share with you that in this course, we've also gotten a compendium ready, and this compendium, again, an idea and a brainchild of Dr. Venkateshwaran, got executed, and it's almost ready for its release. We have we were planning to get the hard copies print on demand ready. However, that will be available for all of us in a while from now. At Vigyan Prasad, we continue to work towards making maths more interesting, more easily understandable, and all that all that kind of fear and the way we all dread mathematics particularly needs to get away, and that's what we are all relentlessly working towards. Not spending much time on all that we need to do and what we have done, I would now pause here and would, because we are all very anxious, very eager to hear Professor Bhargava today. So, with this note, I want to thank and want to congratulate Dr. Venkateshwaran's team of Ramanujam Yatra that consists of Sri Kumar Balakrishnan ji, Mr. Bhaskar, Professor Shastri, and a number of people who worked with us all the while. Thank you so much. And now over to Dr. Ramanujam to take it forward from here. And before I go, Professor Bhargava, it's really nice to see you and to speak with you. An opportunity that we've been looking for a long time gets fulfilled today. And in this course, one last thing, I received a call from Professor Arun Grover of the Punjab Engineering College, and it was very nice to hear about the kind of interactions that you've had with him. And on this moment, would like to also congratulate Punjab Engineering College that's celebrating its centenary as well. So with this, over to Dr. Ramanujam and Professor Bhargav. Thank you once again, and hearty welcome from all of us to this forum. Thank you.
Thank you, Dr. Parashar. It's my pleasure to introduce Professor Manjul Bhargava. It's yeah. I hope you can see the screen now. Yeah, okay. Yeah, Professor Manjul Bhargava is Professor of Mathematics at Princeton University, USA, and also Professor of Number Theory at Leiden University in the Netherlands, and Adjunct Professor at TIFR, IIT Bombay, and University of Hyderabad. He's also the first Distinguished Chair for the Public Dissemination of Mathematics at the National Museum of Mathematics, USA, And I think that's very important to point out here. And he's also an architect of, one of the architects of the National Education Policy 2020. And it's a cliche almost to say that, when you introduce somebody, that he has too many awards and honors for you to list. But I think in Manjul's case, it's actually true. So that's why I had to prepare a PDF to list his honors and awards. He got his Hertz Fellowship as an undergraduate student, and the Hoops Prize, the Morgan Prize. And I think they decided to take a break from giving him awards for a while so that they could resume in 2003. He got the Haas Prize, the Blumenthal Award, the Sastra Ramanujan Prize, the Clay Research Award, the Cole Prize, the Fermat Prize, the Infosys Prize, and the Fields Medal in 2014, and one of the highest civilian honors in India, the Padma Bhushan in 2015. He's a elected member of the American Academy of Arts and Sciences, a fellow of the Royal Society. And lastly, I've added, if and when they constitute an award for the most charming mathematician in the world, it will be Manjul Bhargava who gets it first. So it's a pleasure to have Manjul Bhargava talking to us on Ramanujan's birthday, perhaps the most romantic mathematician of all time. Manjul, over to you.
And thank you so much, Ramanujan-ji, and everyone for the very kind introduction. I hope you can hear me all right. And I just want to take the opportunity to thank all the organizers, all of you for joining. Organizers consist of Vigyan Prasar and Punjab Engineering College, Punjab University, Pi Mathematics Association, Geetam, Kerala School of Mathematics, Ramanujan Mathematical Society, Tata Institute of Fundamental Research in Bengaluru, and the International Center for Theoretical Sciences, ICTS, also in Bengaluru. I'm really grateful to all these organizations for giving me this opportunity to speak on one of my heroes and a hero to so many around India and around the world, Srinivasa Ramanujan. I just want to say it's an honor to be a part of something organized by these organizations who do so much for mathematics and for mathematical outreach. And so it's just an honor to be a small part of that. So thank you very much for all that you do. And thanks to everyone for joining. It's really a great honor. Happy National Mathematics Day. Happy birthday, Ramanujan. I first learned about Ramanujan growing up as a child. My mother used to tell me stories about him. She used to tell me about his mathematics, and that was certainly a great inspiration to me growing up and being inspired to do mathematics. And maybe I'll just share my screen. What I want to do today is tell you a little bit about some of the things in Ramanujan's works that inspired me, some gems of Ramanujan, as I call them, that I think are most accessible to the general public to understand and to appreciate his genius, his creativity. So I'd like to talk a little bit about that, and I'd like to talk a little bit about how some of these elements of his life and of his mathematics were then brought to the silver screen in Hollywood about 5 years ago. So that's what I'd like to talk about today. So as I was saying, I first learned about Ramanujan from my mom, who used to tell me about him, and I was very, very intrigued by his life story and his mathematics. And then later on, when I was in high school, just entering college, this book came out, The Man Who Knew Infinity. And this is a book by Robert Kanigel, who you can see there on the right. He wrote this best-selling biography, which was then translated into numerous languages. And this is the book that really brought Ramanujan into the popular culture in the United States and then around the world. It's a very excellent book. I highly recommend it if you haven't read it before. Very well-researched book. And I read this cover to cover in a matter of one night, a couple nights, and was just completely inspired. I sat with it for a few weeks, trying to understand some of the mathematics in it. And that's what really inspired me to jump into his works and really try to understand some of the incredibly creative things that he did. Also, when I read this book, his life story I found so amazing and his creativity so amazing that it was a dream for me and for many people who read this book that this should one day be a film. I never imagined that one day I'd get to be a part of trying to launch such a film. But it is really an incredible life story. I highly recommend reading this book and or watching the film, which I'll tell you a little bit more about. So about 5 years ago, this book was made into a film by the same name, The Man Who Knew Infinity. And it was played by Dev Patel, who was formerly famous for Slumdog Millionaire. And now he played Ramanujan. And so this is just a still from the movie when he was in Cambridge. So I'll tell you a little bit more about that in a little bit. So Ramanujan was born in 1887 in Pallipalayam in the region of the Kaveri River. So he grew up in Kumbakonam in Tamil Nadu in southern India, near the Kaveri River, which is a real center of the arts and music and culture. Not surprisingly, many great scholars come from that region, and Ramanujan was one of the most illustrious of the many illustrious scholars that came from that region and continue to come from that region because it is such an artistic and cultured musical place. In particular, Ramanujan's mother was a classical Carnatic singer. And so that was the atmosphere in the home, that there was music going on. There was also a local temple where drums, the double drums were always playing, where Ramanujan used to like to sit and listen to the drums as he thought about mathematics. And that's something that I, of course, relate with a lot. I spend a lot of time thinking about mathematics while engaging with the classical percussion tradition of India, drumming tradition of India. So it won't be surprising that Ramanujan was an outstanding student. He won many academic awards, and he earned a scholarship to college. His family was quite poor, so earning a scholarship to college was a very big deal. It made college possible. But of course, the mathematics courses that he got in school and in college were not so challenging for him, and so he did most of his mathematical explorations on his own from school onwards. In particular, he discovered much of trigonometry by himself as a 13-year-old. And then later on, when trigonometry came up in school, he was disappointed to know that the subject was already known. And this is something that happened many times throughout his life. He would discover entire fields, entire theories, only to learn that these were already known. So he was always far ahead of what was being taught to him in school. Ramanujan started to spend all his time on mathematics as school progressed. And as he entered college, he was just spending all his time on mathematics. So much so that as a result, he flunked out of college twice because he was spending so many hours in his temple lobby listening to the double drums as he did his mathematics. And he was proving new theorems every day. And that just inspired him to do more and more and more. And he was just spending all his hours doing mathematics, discovering incredible things. He worked on mathematics a lot in his home as well, where 6 people lived in one room. So that's the poverty that Ramanujan grew up in. 6 of his family members lived in one room. We often joke here in Princeton and in many universities around the world, lots of people complain, oh, I have to share an office with somebody. But here Ramanujan was not having an office, just a windowsill on which he worked in a room that was shared with 6 people. And he was producing incredible theorems, doing so much productive work, doing more in a day that all of us wish to do in a year. And so this is the hardship that he went through, but despite that hardship was producing incredible things. He used to say that his findings came as visions from his hometown goddess Namagiri. And this really is the best explanation for some of the things that he came up with. We just can't understand how he would come up with such things. he definitely had some kind of connection with the divine mathematics that we still don't understand how he used to come up with these things in a normal mortal way. To alleviate the poverty that his family lived in, he found a job doing clerical work. So since he flunked out of college and his family was in poverty, he took up a job as a clerk. And so he would do this clerical work during the day, and then all other free hours in the evening and night were spent doing mathematics. Unfortunately, no one could really understand locally what he was doing. He was doing quite complicated things. Local mathematicians could tell that he had some incredible talent, but they could not really understand what he was doing. And many even termed him a crank because he was producing things that no one could understand. Luckily, he had a very supportive family. He had a very supportive neighborhood. His friends were very supportive, and they said, maybe you need to go out of your local area to find someone who can understand your mathematics. And they encouraged him to write to mathematicians around India and also around the world in the hope that someone out there could understand his mathematics. And he started writing to mathematicians around the world. And as you can imagine, most mathematicians, when they heard from a clerk in India who had no college degree and was writing things that they could not comprehend, they generally took the letter and assumed it was from a crank and threw it in the garbage. But there was one mathematician who did not throw it in the garbage because he recognized something in those letters that no one else saw. And that mathematician was G.H. Hardy. And I just want to share with you a few lines from the beginning of the letter that Ramanujan wrote to Hardy, just so you can see why most mathematicians would just throw his letter straight in the garbage. So Ramanujan writes to Hardy. The first line is, "I beg to introduce myself to you as a clerk." Now you can imagine if a mathematician receives a letter saying, "I've proven some amazing mathematical things. I am a clerk without a college degree." Most people would throw that straight in the garbage. Credit to Hardy that he did not throw it out right here. "I beg to introduce myself to you as a clerk." Next line, "I have had no university education." So again, Ramanujan, being his usual humble self, was saying these things, and as you might imagine, most people would not take this too seriously. So again, credit to Hardy that he did not throw it out even at this point. And Ramanujan continues to write, "I have not trodden through the conventional regular course, but I am striking out a new path for myself. And the results I get are termed by local mathematicians as startling." Luckily, he was not too precise about what he meant by startling. That can be taken in a number of ways. But Hardy read this and he said, okay, let me just take a look. So here on the left is a picture of G.H. Hardy, who is one of the great number theorists at the time, an expert in analytic number theory. He was at Cambridge University, Trinity College. And on the right there, you can see Jeremy Irons, who plays G.H. Hardy in the film The Man Who Knew Infinity. And as you can see, there's quite a resemblance. I think in this generation, people will now think of G.H. Hardy as Jeremy Irons. So Jeremy Irons is the Academy Award winner actor who's there on the right, who really did a tremendous job playing G.H. Hardy and also looking like him. So, okay, so I told you the first few lines, what was written in the letter, but then he gets on to some mathematics. What was in the letter? Here's something Ramanujan wrote in his letters that made people think he might be a bit crazy. One of his first formulas that he writes in his letter is the following. 1 + 2 + 3 + 4 + 5 + ... So if you add up all the positive integers, Ramanujan says, you get -1/12. Now, what on earth could that mean? As you can imagine, if people made it to the mathematics in reading Ramanujan's letter, they would definitely throw it out at this point. However, Hardy recognized that this formula is not something crazy, but is actually something deep. Hardy recognized this immediately as the theory of analytic continuation. If you've taken complex analysis, or if you get to take complex analysis in the future, you learn that there's a function called the Riemann Zeta function that has an analytic continuation. And there is a meaning to adding the positive integers, which means just evaluating the Riemann Zeta function at a place where it doesn't converge, but where it does have a value due to the analytic continuation of the Riemann Zeta function. So the left side here, the sum of the positive integers, can be viewed as zeta of -1. And the value that you get when you analytically continue the Riemann Zeta function to -1 and beyond is -1/12. And so Hardy recognized this as a deep formula that tells you a value of the analytically continued Riemann Zeta function. This is totally amazing because earlier in the letter, Ramanujan said that he does not even have a college degree. In particular, he did not know the theory of complex analysis, of analytic continuation, yet he was writing down formulas that made it seem like he must know all this stuff. So he was coming at it in a completely different way than anyone was used to, because he was not using the standard theory that one learns in college and in higher mathematics. How is he coming up with this? This was very intriguing to Hardy. But Ramanujan had finally perhaps found someone who understood him. That was very exciting, that Hardy did not put it down. He actually understood some of the things that were being said in there, in his letter. Hardy continued to read, and there was some other stuff from out of this world. So let me tell you one of the things that really intrigued Hardy. Hardy was an expert on problems of this kind, and yet he had never seen anyone do the kind of work in this area ever before. So here's one thing that intrigued Hardy right away, and I'd love to tell you a little bit about it. It's actually fairly easy to understand. So Ramanujan defined what's called a continued fraction, a certain continued fraction, this one. So it's a function of q, r of q. He said, let r of q equal this fraction where you keep dividing and then adding and dividing and adding. So r of q is equal to 1 divided by 1 plus q over 1 plus q squared over 1 plus q cubed over 1 plus, and so on, all the way to infinity. So Ramanujan defined this function of q, r of q. So where those numerators are growing like 1, q, q squared, q cubed, and so on to infinity. Now, people have studied continued fractions for a long time. And the case q equals 1 is actually a very well-known continued fraction. 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus ... That's a very famous continued fraction. It's a famous fact that r of 1, when you plug in q equals 1 there, you get square root of 5 minus 1 over 2. In other words, the golden ratio. This is a famous expression for the golden ratio, which occurs, of course, all over nature and all over mathematics. And how do you prove that? R of 1 is well known to be the golden ratio, and the way you evaluate that is very standard. So you plug in, if you just look at this function r of q and just plug in q equals 1, you'll notice that if you see, you have here 1 over 1 plus 1 over 1 plus 1 over 1 plus, and so on. If you look at just this part, 1 over 1 plus this expression, 1 over 1 plus blank, this blank is just the same value as the original continued fraction, r of 1, right? When q is 1, this part here is the same as the whole thing. It's like a fractal. So what that means is that if you let r of 1 equal x over here, we see that x is equal to 1 over 1 plus x. This is the same expression here. So x is equal to 1 over 1 plus x. And now you just solve for x, and you find that you get minus 1 plus square root of 5 over 2. So I did that a little quickly, but definitely try that out. Show that when you have q equals 1, that this is just the golden ratio, minus 1 plus square root of 5 over 2. Okay? And that you do by just noticing that this expression here is just itself. So x is equal to 1 over 1 plus x. So that's how you evaluate r of 1. But that trick, which is standard in the theory of continued fractions, does not apply when q is not equal to 1, because these numbers keep changing as you go down. And so it's not quite a copy of itself when you start going down. In fact, it's not a copy of itself at all. And so how do you evaluate such a thing that goes to infinity when you don't even see a copy of itself going down? So this is a kind of continued fraction that no one ever knew how to evaluate. And so Ramanujan asked in his letter, is it possible to evaluate R of Q for other values of Q? That's a natural question that comes from this very natural continued fraction. And Ramanujan claimed that he could actually evaluate this at values other than 1. And not just at any value, but in some very peculiar values that immediately intrigued Hardy. Ramanujan claimed that he could plug in Q equals e to the minus 2 pi. Now just imagine, he's not saying Q equals 2, he's not saying Q equals 3, he's saying, I'm going to evaluate it at Q equals e to the minus 2 pi. E is a transcendental number, 2.7182818.28459, right? It's an infinitely expanding non-periodic decimal expansion. It's not even algebraic, it's a transcendental number, so is pi. And he's going to take e and raise it to the minus 2 pi, 2 of the fundamental constants. And he's going to evaluate it there. And he says, I can evaluate it. And the answer comes out to be this amazing expression, e to the 2 pi over 5 times something that looks like the golden ratio. Again, the answer also involves both e and pi and the golden ratio. This is, for mathematicians, one of the most beautiful kind of equations that can come up, because it involves a beautiful expression, and it's being evaluated at something that involves 2 of the most fundamental constants of nature, e and pi. E comes up when you're computing interest, pi comes up from circles, and the answer involves e and pi and the golden ratio, 3 of mathematics' most fundamental constants, all in one equation. I mean, what could be more beautiful than that? The fact that this is true is already really beautiful, but the fact that someone can prove this, that's what was so intriguing to Hardy. Hardy had never seen anything like it before. He saw no way that one could actually prove something like this. And then Ramanujan made a further unbelievable claim, is that he said, I can evaluate R of e to the minus pi square root of n for any positive rational number n. And he stated that claim without proof. But he gave these examples which showed that he clearly had some techniques that no one had ever seen before. This completely stunned Hardy when he read this, and it's really, again, credit to him that he read this far to look at this and realize that there was something really incredible going on here, being done by a clerk in Madras. Hardy's reaction, Hardy writes in his autobiography years later, he writes, these formulas defeated me completely. I had never seen anything in the least like this before. They could only be written down by a mathematician of the highest class. They must be true because no one would have the imagination to invent them. So he said there's got to be true, because who could have such a creative imagination to invent something like this? If he's writing it down, it must be true. and he was right. Ramanujan was correct about that formula and many others that he had written in the letter. And Hardy recognized the genius of them. And he decided that he had to bring Ramanujan to Cambridge and try and understand how he was coming up with these things. As I said, I had the privilege of being an associate producer, mathematical consultant on the movie The Man Who Knew Infinity. This was, of course, a moment in Hardy's life that, and Ramanujan's life, that had to be portrayed in the film. One of my jobs was to make sure that the mathematics in the film was correct, so I can assure you that the mathematics in the film is correct. And I thought I'll show you a clip of how Hardy reacted after he got Ramanujan's letter. He realized that it must be a mathematician of the highest class, but it was hard to believe that it could have been written by somebody who was not college educated. And so the only other conclusion was that maybe it was a prank. And his good friend in Cambridge Professor Littlewood, another great number theorist of the time. They were very close. They used to play pranks on each other. Hardy thought maybe this is a prank being played by his colleague, Professor Littlewood. So here's a scene from the film where Hardy has just received the letter. He has studied it for a while and is completely stumped. And now he's playing a game with racket game with Littlewood, and I'll just play this clip for you.
You know, Littlewood, this year alone, I've received correspondence from those who profess to prove the prophetic wisdom of the pyramids, the revelations of the elders of Zion, and the cryptograms which Bacon supposedly buried within the plays of the so-called Shakespeare. But a letter from an ill-educated Indian clerk in Madras challenging assertions I made in the track series really takes the biscuit.
Well, I have to say, I've made similar assertions myself.
So you admit it?
But this was 3 years ago.
No, I'm talking about the letter. Bloody brilliant, I thought. I don't know where you got the postmark. Almost had me fooled.
I simply don't know what you're talking about.
Oh, come on. I'm not a complete idiot.
I don't know how to get this into your thick skull, but whatever it is you're talking about, I'm simply not involved. Play.
So, you've missed Hall.
Not hungry. I tell you, there is a war coming, no doubt about it. Because we are being led like mindless, spineless sheep. No one bothers to question any of it. It's coming all right, you can smell it.
You're as paranoid as Hardy.
With all due respect, Bertie, you couldn't hold a candle. Littlewood, could I have a word?
Yes, of course. Integrals, infinite series, God knows what else. Oh, excuse me. Always forget you don't believe in a supreme being.
All right.
Well, this chap turns out to be genuine. You might have to reconsider.
Oh, he must be genuine. Who'd have the imagination to invent all that?
Well, I'm rather flattered you thought I did. These two infinite series are the more intriguing.
Yeah, they defeated me completely. I've never seen anything like them.
Well, it's deceptive. I'll wager the hypergeometric series.
A great Littlewood stumped. He's Hobbes class, I'd say. Being inexperienced, I would very highly value any advice you give me. Yours truly, S. Ramanujan.
What does the S stand for?
You can ask him yourself.
You intend to invite him here?
Well, no. Much better let him rot away in his office in Madras.
As you can see at the end of that clip, Hardy decided that he must get Ramanujan to come to Cambridge. And that he did. He invited Ramanujan to come to Cambridge. He got a lot of backlash in Cambridge, obviously. Indians were generally not invited to Cambridge. Certainly not those who had not even had a university degree were considered uneducated. So he got a lot of backlash, but Hardy had a lot of stature there in Cambridge. He managed to get the invitation out for Ramanujan to come over to Cambridge. Of course, Ramanujan, similarly back in India, had trouble convincing his family that he should go to Cambridge. But he explained, this is the one person in the world that seems to understand what I'm doing, or at least understands the value of what I'm doing. And so he convinced his family that he will cross the seas, go to Imperial England to work with this great mathematician, Hardy. And he did eventually cross the seas and come to Cambridge. And they had one of the most productive collaborations of all time. It wasn't easy. Ramanujan taught a lot to Hardy about the value of intuition and coming to great theorems just by pursuing beauty and intuition and pure thought. Whereas Hardy was a stickler for rigor and taught Ramanujan and really encouraged and almost forced Ramanujan to learn the way of conventional thinking so that he could explain his work to them. And there's a lot of debate on whether this slowed down Ramanujan. If he wasn't slowed down by these requirements of rigor, whether he would have taken off even more, or whether it would have been better to just leave him alone and let him fly, or was it better to force this rigor on him? It's still debated today. But here's a clip from the movie where they discuss this issue. I'll show you a couple of clips where they discuss this issue on whether Ramanujan should be spending all his time on these proofs or whether he should continue to just produce his incredible results. So this is a clip from when Ramanujan first arrives in Cambridge and is meeting Hardy and Littlewood. And Hardy and Littlewood want him to take some courses so that he can talk in the conventional manner that they do. So here's a clip that shows that.
Ramanujan, we decided that for the good of everybody, you should attend some lectures.
But I'm here to publish.
Yes, all in good time, I hope. But first we need proofs of your work.
It's really nothing to worry about. It's simply a question acquainting you with the more formal methods that will benefit our future work together.
I mean, we need a common language. You wouldn't expect us to converse with you in Tamil.
No, but you expect me to speak English.
Quite. So, there'll be plenty of time for publishing.
I'm sorry, but with all humility, how does anyone know that? I don't want this to die with me.
I'm sure you it would.
Thank you, sir. But I have much more to share with you. As I told you, the letter only contained a small sampling of my discoveries. You'll see I have even found a function which exactly represents the number of prime numbers less than x in the form of an infinite series.
Exactly.
Yes, I thought if we were going to publish, it should be something groundbreaking.
This is most unexpected.
Hardy, this will take a lifetime.
Maybe two.
So as you see in the clip, Hardy and Littlewood realized that Ramanujan had brought just an incredible amount of mathematics with him to Cambridge, and how on earth were they ever going to understand it? And Hardy started forcing Ramanujan more and more to learn the conventional way of proof, the conventional rigor, so that he could try and explain it to Hardy and to Littlewood and to his mathematical community. And of course, for Ramanujan, this was very difficult because he had these flights of fancy. He was coming up with things where he didn't need to know the usual complex analysis. He had his own way of thinking about things. And he was being forced into slowing down in order to prove things, in order to explain them to Hardy and his colleagues there. And that was very tough on him because he loved to move quickly and prove new things every day. And so here's the clip where Hardy explains why this is important for him to slow down and pursue the conventional rigor so that people can understand him. So this is a clip about that.
How did you know that theorem?
It came to me. Mr. Hardy, I don't understand why we waste our time doing all these proofs. I have the formulas.
It's not that I can't see what you've claimed. It's that I'm not sure that you know how you got there, or indeed that your claims are correct. There are subtleties which...
But they are right, sir. I have more important new ideas.
Yes, but intuition is not enough. It has to be held accountable. And a little humility would go a long way. Why do you think they want us to fail?
Because I'm Indian.
Well, yeah, there is that. But also because of what we represent. Now, Euler and Jacobi, who were they?
Mathematicians.
Just names to you. Euler was the most productive mathematician of the 18th century. Most of his work done after he was blind. Jacobi, like you, was snatched from obscurity and was almost as impressive as Euler. Now, I think you are in their class. What they had in common, what I see in you, is a love of form. It's all through your notebooks. Let me ask you something. Why do you do it, any of this?
Because I have to. I see it.
Like Euler. Form for its own sake. An art unto itself. And like all art, it reflects truth. It's the only truth I know. It's my church. And you, just as Mozart could hear an entire symphony in his head, you dance with numbers to infinity. But this dance, this art, does little to endear us to certain factions who see us as mere conjurers. So if we are going to challenge areas of mathematics that are so well trod, we cannot afford to be wrong. I need you to attend your lectures, don't offend your professors, and keep doing your proofs. Otherwise, this experiment of ours will be doomed to failure. Come with me. I want to show you something. There are many ways to be honored in life. For us, being elected a fellow is certainly one, but in my humble opinion, to leave a legacy here at the Wren after we're gone is the greatest. This library houses the epistles of St. Paul, the poems of Milton, Morgan's Bible. But in my estimation, as a man of numbers, the pièce de résistance is Newton's Principia Mathematica. Now, just as Newton represents the physical aspect of our work, your notebooks represent the abstract. It took a long time for Newton to be proved, which is why we have an obligation to prove these. And if we do, I believe that one day, these notebooks will find their place here. Now, do you understand what's at stake here? Good.
Hardy was correct that Ramanujan's work would one day be displayed in the Wren Library next to Newton's works. Hardy could see that talent in Ramanujan, and he was right. And they gradually brought each other towards their points of view. And they had one of the most productive collaborations of all time. Ramanujan spent 5 years in Cambridge, one of the most productive collaborations ever. During his visit, Ramanujan wrote 30 papers, some on his own and some joint with Hardy. And many of them really transformed the fields in which they were written about. So just some remarkable papers, which really transformed the field of number theory in many ways and beyond number theory. But it was not an easy time for Ramanujan at all. He had to overcome some severe hardships, extensive racism, the fact that World War I started when he was there, which meant that he could not go home in between. His wife couldn't come over. And one of the hardest things for him there, if any of you have had English food, you can understand this. English food not terribly spicy. It's not traditionally very vegetarian. So when Ramanujan was there in Cambridge, he was having trouble getting food. It was hard to find even potatoes that were not cooked in lard. And of course, even when you could find vegetarian food, it was not of the taste that he wanted. English food cannot satisfy a South Indian palate. And so, despite Hardy being a very good mathematical host, it turns out he was not a very good host in any other sense. He devoted his life to mathematics. He did not know how to be hospitable in a personal way. And as a result of that, Hardy was completely unaware that Ramanujan did not have adequate clothing. He came from South India. He had clothes that were he was not used to wearing warm clothes. He didn't have them. Hardy had no idea that he was cold all night, that he was malnourished, not getting very much food. And so he was they were both just working on mathematics, and Hardy was completely unaware of these hardships that Ramanujan was facing. Despite these hardships, for his field-changing work, he was elected Fellow of the Royal Society, which at that time was the highest honor that could be given to a mathematician and to a scientist. But they did about 5 years of work. When the war was over, Ramanujan did go back home, but having suffered severe malnutrition for 5 years, he fell very ill even before he returned home, and he was basically in bed that last year of his life, where he did at least get reunited with his wife, with his family, with his mother, but he only lasted 1 year there after severe illness due to malnutrition. He died a year later in 1920 at the age of 32. Mathematicians continue to think about this great tragedy. As I'd mentioned before, Ramanujan was not college educated. And so when he was doing his mathematics, the first several years, he was just rediscovering things that people already knew, entire theories that people already knew. He was just hitting his stride at around 30, when he was proving things that were completely new and not connected to things that were previously known. And even just in those 2-3 years, those last years of his life, he contributed so many things that transformed mathematics. And one just wonders where mathematics would be had he lived to a normal age. I mean, it would have been just incredible. And I was mentioning before how people still debate whether it was correct of Hardy to slow down Ramanujan in order to prove some of the things that he was doing. Well, at the time, Hardy didn't know that he was only going to get a few years with Ramanujan. If Ramanujan had his whole lifetime, sure, why not learn the conventional way of doing things too? But given that he only had a few years, maybe it would have been better to let Ramanujan fly and produce lots of things. We could have taken care of the proofs later. Mathematicians would be there to work on his things. So these are the kinds of debates that go on. But of course, the best situation would have been that he would have had food and clothing while he was there in Cambridge. If the World War I had not come, so that his wife could have come, and he would have had family, he would have had food, or if he could have gone back home in between if World War I wasn't going on. So it's just things really aligned in a way that were that caused this tragedy. And yeah, we all wonder what mathematics would have been like had he been able to live to a normal age. But even when he was on his deathbed, his last year of life back in India, he continued to produce mind-blowing mathematics and just unbelievable stuff on his deathbed, some of which we're still trying to understand, and some of which is continuing to transform mathematics, which we're still trying to understand today. And I'll explain some of his last letter in a little bit. The last letter that he wrote to Hardy. So what can we learn from Ramanujan's story? Well, there are sort of two answers. The first answer is, of course, Ramanujan's mathematical legacy. His ideas have inspired and continue to inspire generations of mathematicians. His works have been heavily influencing the work of, that led to two Fields medals. Of course, Deligne's proof of the Weil conjectures, which in particular were inspired by conjectures of Ramanujan. Monstrous moonshine of Borchards, his proof was also inspired by ideas of Ramanujan. And of course, the proof of Fermat's last theorem by Wiles, many ideas that go into it, including things behind Sayre's conjecture, were inspired by Ramanujan. So some of the greatest works that have really driven 20th century mathematics originated in ideas of Ramanujan, or were driven by conjectures and ideas that Ramanujan had. They heavily influenced 20th century mathematics. These are just three examples. But maybe even bigger than that, there's a broader legacy that Ramanujan leaves, which I think is really important to learn from his story. That broader legacy is that talent can really be found anywhere, regardless of background or economic status, regardless of geographical location. There is talent. We could easily have missed Ramanujan's talent. There are some lucky things that happen there, a recognition by Hardy of that talent. But it easily could have gone unnoticed. And what a tragedy that would have been. But the truth is that these kinds of tragedies are happening all the time. We have talent all over India. We have talent all over the world, in areas of poverty, in areas that have lesser economic status. And to fulfill the potential of this talent, it has to be located, it has to be recognized, and it has to be nurtured, it has to be fostered. That is extremely important. And that's what really suggests that we have to have universal education for everybody. Everybody should have access to education so that they can fulfill their talents. And education policy was mentioned earlier. I think the goal of any education policy has to be that every single person gets education from whenever they can start, from the age of 3, even early childhood education, all the way through university education. It should be universally accessible so that we never lose talent of this kind. So that's very, very important. I want everyone to always keep that in mind, that we have to do everything we can to make sure that no one is left behind in the realm of education. So that's something broader that we can learn from Ramanujan, that talent really can be found everywhere and can be found anywhere, and we have to be there to foster it. Okay, so I want to conclude by talking about 3 of my favorite gems, mathematical gems that Ramanujan left us. Most of his work is not so easily accessible, of course, to the public, but there are some things that really are. And these are 3 things that I think anyone can really understand and appreciate the creativity that Ramanujan had. So here's the first gem. Ramanujan loved partitions. It's one of the most elementary number theoretic things that one can define. So what is a partition? It's a function, and I'll define it with an example. We say that P of 4 is equal to 5 because we can partition 4 in exactly 5 ways. So what do we mean by that? Well, 4 can be broken up into pieces in exactly 5 ways. You can write 4 as 4, but you can break it up as 3 plus 1. You can write it as 2 plus 2. You can write it as 2 plus 1 plus 1, or you can write it as 1 plus 1 plus 1 plus 1. So there are 5 ways that you can break down 4, right, into pieces. So similarly, P of 1 is 1. Why? Because, well, 1 can be broken down in exactly one way, right? You can just write 1 as 1. But 2, you can write as 2, or you can write as 1 plus 1, right? So there are two ways. So P of 2 is 2. P of 3, if you think about it, is equal to 3, because you can write 3 as 3. You can write it as 2 plus 1, or you can write it as 1 plus 1 plus 1. So P of 3 is 3. So these three values, it looks like there's a pattern. But then, of course, that pattern breaks at 4, as we already saw. P of 4 is equal to 5. And, well, you can continue working out values of P. If you look at P of 8, it turns out 8 can be broken down in 22 ways. P of 16 is 231, as I'm sure you guessed. P of 32 is 8349. Everyone see that? So these numbers look kind of random, and they are. They don't have an easy pattern. P of 64 is over 1 million, and then P of 128 starts to get even bigger, even faster. P of 256 is that. And if you don't see the pattern, you're not alone. People studied this for a long time and could not see even how quickly these numbers are growing with n. If you're looking at P of n, how fast does P of n grow with n? In other words, how fast are these numbers growing? As you increase what you're breaking down, the number of ways to break it down seems to grow pretty fast. How fast does it grow? Even that question was unsolved. So this very basic question about how many ways you can take a number and break it down into pieces, it was not understood how fast that grows. How fast is the number of ways that you can break down a number into pieces? How fast does that grow? That was a long time unsolved problem. How does P of n grow as n grows? So this question was one that Ramanujan thought quite a bit about, and he came up with how P of n grows, a formula that completely took all mathematicians by surprise. Let me show you that formula. It's just incredible. For the first time in history, Ramanujan came up with an asymptotic formula for the number of ways that you can break up n into parts, a formula for P of n. And here's his formula, which he then proved in conjunction with Hardy. So Ramanujan's formula was that P of n grows like 1 over 4n square root of 3 times e to the pi. Notice e's and pi's appearing again. Ramanujan had this talent of producing these incredibly unexpected occurrences of e and pi. But his answer was that P of n grows like 1 over 4n square root of 3 times e to the pi square root of 2n over 3. This is one of the most beautiful formulas in all of mathematics. We're taking the most basic function. How many ways can you break up a number into pieces? And we're saying it grows like something that involves two of these fundamental constants of mathematics. An absolutely incredible formula. And you can see it's kind of growing exponentially, but only exponential in the square root of n. But the constants that are coming up are just incredible, e and pi. Hardy was floored when Ramanujan first presented this to him. And they spent much of their time in Cambridge trying to prove Ramanujan's formula. And in the process, so this formula, of course, completely surprised all the experts. But what's more, it's not just the formula that's so important here, but the method that Ramanujan developed in conjunction with Hardy to prove this. It was written about in a letter from Ramanujan to Hardy, which he called the circle method. And so this problem actually marked the birth of what's now called the circle method, which is the fundamental tool of analytic number theory today. And it first came up in this most basic problem, and now it's completely transformed the area of analytic number theory. So I just love how such a fundamental tool in theory came about through such an elementary and beautiful problem, which had one of the most beautiful answers in that formula. It's just absolutely incredible, incredibly creative, but incredibly transformative to mathematics. So that's my first gem for you. Second gem is one that's very well known. It's called the taxi cab number. So Hardy writes in his autobiography that I remember once going to see Ramanujan when he was ill at Putney. I had ridden in taxicab number 1729 and remarked to Ramanujan that the number seemed to me rather a dull one. He was just trying to make conversation when Ramanujan was ill. Ramanujan's there ill on his bed, and he says, no, it is a very interesting number. So Ramanujan immediately, his eyes light up, and he says, it's a very interesting number. It's the smallest number expressible as the sum of two cubes in two different ways. So here, Hardy's saying, trying to make conversation, no, it's not a very interesting number. And Ramanujan immediately gets excited and says, no, it's a very interesting number. It's the smallest number expressible as the sum of two cubes in two different ways. And of course, he was right. 1729 can be written as 1728 plus 1, which is 12 cubed plus 1 cubed. But it can also be written as 1000 plus 729, which is 10 cubed plus 9 cubed. And so this is the smallest number that's expressible as a sum of two cubes in two different ways. It's stories like this that led Littlewood to remark that every positive integer is a personal friend of Ramanujan. Ramanujan saw beauty in every number, and he was personal friends with every number. That was how Littlewood expressed Ramanujan's incredible intuition and closeness with all numbers. So I love this story, not just because he just knew this thing about 1729 right away, but the fact that it's expressible as a sum of two cubes in two different ways have actually, that story has actually motivated a lot of mathematics. There's a whole number of papers that study variations of this problem, and they're called taxicab numbers after the story. But also beyond that, it's motivated study of K3 surfaces, and it connects to actually a lot of deep mathematics, this problem. So that's why the story is so incredible. And that seems to happen a lot around the work of Ramanujan, that it looks like he writes down these random looking things, and then it turns out that this is actually very fundamental in a number of other mathematical problems. The final thing I want to show you is yet another example of that, where people thought Ramanujan is writing down some random things, and then it turns out to be fundamental 80 years later. So this occurs in the last letter that Ramanujan wrote to Hardy. On his deathbed, this is the kind of stuff that he was coming up with on his deathbed. He writes, Dear Hardy, I am extremely sorry for not writing you a single letter up to now. There he is on his deathbed, apologizing for not writing more mathematics. I'm extremely sorry for not writing you a single letter up to now. I discovered very interesting functions recently, which I call Mach theta functions. They enter into mathematics as beautifully as the ordinary theta functions, and so on. Theta functions have been one of the most fundamental functions in mathematics. They're first examples of what are called modular forms, which are all over mathematics and physics. And here is Ramanujan writing to Hardy that he's found something called Mach theta functions, which he's claiming enter into mathematics as beautifully as the ordinary theta functions. Just on his own, on his deathbed, he makes this claim. And here's a copy of that letter. You can see these incredible series that he's written down that he's claiming are going to enter into mathematics as centrally as ordinary theta functions. And given that he had limited time, he wasn't proving very much about these. He was just saying, here they are. Here are some incredible functions. They have all sorts of properties, and this letter never really got noticed for years. People thought, okay, he was on his deathbed. He's writing down some random functions. He's made a very tall claim about them, but who knows? And 80 years went by, and nobody really made much sense of these. And then, so it was a mystery until the 2002 PhD thesis of Zwegers, who showed that Ramanujan had actually discovered what are now called mass forms. And Ramanujan was right. These kinds of forms enter into mathematics as beautifully as theta functions. And these mock modular forms have been living up to Ramanujan's expectations. Since 2002, there's been a deluge of work on these mock theta functions. They've been connected to monstrous moonshine. They are being studied both by mathematicians and by physicists. It turns out that to understand certain properties of entropy of black holes in string theory, certain kinds of functions were needed that had certain properties to understand that problem. And it turns out this letter had exactly what was needed. And now mock modular forms are being studied heavily years later. One of the endnotes in the film is this one. A century later, these formulas are being used to understand the behavior of black holes. It's just incredible, the foresight that Ramanujan had. He obviously did not know about entropy of black holes, but he knew that this was important. And now it's entered into areas that we never imagined 80 years ago, 100 years ago, that these objects would be so important. And that happens so often throughout Ramanujan's notebooks that we understand a new line of his notebook. We can prove almost everything in his notebooks now, but what the items in his notebooks really mean, often it takes decades to appreciate, and that's still happening today. So that really is the story of Ramanujan. We're still trying to understand a lot of the things that he wrote down. Some of the things that he wrote down were inspirations for me personally in the mathematics that I do. So it's just an incredible story. One of the most amazing people to have ever lived. And I'm honored to have had the chance to tell the story to the public through this film, The Man Who Knew Infinity, which was a low budget film, but it was one of the highest grossing independent films that year. And I just hope that more people can learn about his story, be inspired by him. He shows that talent is everywhere, anywhere, and that if you're passionate about what you do, then you can achieve great things despite the greatest hardships. So very inspirational person in mathematics and in life. And I just want to end by I'll show you the trailer for the film. And yes, please go and read The Man Who Knew Infinity, watch this film, but most of all, be inspired to do great things, do great mathematics. And I'll stop there and just show you the trailer.
What do you see?
Sand.
Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything.
Integrals, infinite series.
I've never seen anything like them. From an Indian clerk, ill-educated in Madras, I would very highly value any advice you give me.
Letter for you. Postmarked to England.
Yours truly, S. Ramanujan.
What does the S stand for?
You can ask himself.
We intend to invite him here.
Don't forget me. I could never.
Are you Ramanujan by chance? Oh, don't be intimidated. Great knowledge comes from the humblest of origins.
For the good of everybody, you should attend some lectures.
I'm here to publish. The letter only contained a small sampling of my discoveries.
This will take a lifetime.
Maybe two.
We need proofs of your work.
But they are right, sir.
I hadn't completed that proof. How do you know?
I just do.
You don't pull a stunt like that in my class.
Get out!
How do you know that theorem?
It came to me. These steps you want, I do not know how to do.
Where do you think you're going? It's our home.
Don't you know what I've given up to be here? I have nothing. You wanted to know how I get my ideas. God speaks to me.
There are no proofs. We're just supposed to take him at his word?
No, you're to take him at mine. Why do you do it?
Because I have to.
proofs that can determine the outcome of matters of the heart. We are merely explorers of infinity in the pursuit of absolute perfection.
I owe you so much.
No, no. It's I who owe you.
Well, thank you so much, everybody. It's been a great honor to be able to talk to you. I'm open to take a few questions, but thank you again. Thank you so much for having me. Really appreciate it.
Thank you for that wonderful presentation, Professor Bhargava, and an inspiring lecture on an inspiring figure in history of mathematics. Venkateshwaran, will you start on questions?
Yeah, I think there are some few questions which have come. I mean, quite a lot of questions actually. I mean, if we take all of them, it will be a bit impossible. But a few have been selected. And Srikwa, can you flash those questions here on the screen?
The first one is very long. Maybe I will just read it out.
Yeah.
This is from Ravinder Banyal. He says, Ramanujan was a deep thinker by his own accord. His mind was constantly engrossed in the abstract world of mathematics. It's not hard to imagine intuition playing a profound role when a person is deeply engaged with the subject. When we say his work was inspired by some sort of divine vision, wouldn't it amount to undermining his rich legacy and mathematical accomplishments? He's asking you, Manjul. I mean,
this is a very tough question. The divine intervention was, of course, the way that Ramanujan himself interpreted it. But of course, it's up to us to decide where we want to see his inspiration. The answer for his inspiration, of course, is all of the above. It was hard work. It was lucid dreams, which he interpreted as coming from divine intervention. But you're absolutely right. I mean, his creativity was out of this world, and yes, all credit to him for staying passionate, for working hard, and for being just an incredibly creative mind. There's no doubt about that. We're not ever going to try to undermine that. That is indubitable that he had just incredible creativity, and it should inspire us to be able to think outside the box the way he did. That's constant inspiration for me as well, and it should be for all of us.
The next one? Yeah. Okay, this is by Vatsal Srivastava, who's asking, do we know any algorithm to compute R of e to the minus pi square root of n that you were referring to for the continued fraction for e to the minus pi square root of n? Vatsal Srivastava is asking whether there is any algorithm to compute.
Yes, there is. I think it's only been understood fairly recently, although I myself am not. I couldn't be able to. Well, I wouldn't be able to tell it to you in a short amount of time. But I believe the answer is yes, and it is inspired by the foundations that were laid by Ramanujan.
Another question by Gautam Borisagar. If time permits, I would like to know: is there any result which Ramanujan was wrong and corrected later? In which Ramanujan was wrong and it was corrected later.
Yes, there have been a few mistakes that Ramanujan made. The vast majority of the things he wrote down were correct, which is just absolutely incredible, given that he was writing about things that, by conventional standards, he had not learned the background material necessary to be able to make such claims. And the vast majority of things that he wrote down were correct. But every once in a while, he did write some things that were not quite correct. And when he did, those mistakes were actually quite amazing. They would, the corrections of those mistakes would involve understanding and unraveling something very deep. So some of his there's one famous mistake that he made that inspired my own work, which was he wrote down a set of quadratic forms that represent every positive integer, but one of those quadratic forms was wrong. It didn't represent every integer. It didn't represent the number 15. And this mistake was part of the inspiration behind Conway and Schneeberger's 15 theorem. It says that an integer matrix quadratic form represents every integer if and only if it represents every number up to 15. And it's kind of amazing that that mistake that Ramanujan made involved the number 15 in quadratic form. So that's kind of, those kinds of mistakes often happened. And that's the mistake that inspired my own work with Jonathan Henke on proving a result called the 290 theorem. So that's one example of a mistake. Some of his other mistakes are also really incredible. They, in some form or another, some of them involved not knowing the Riemann hypothesis. Of course, he had not learned about the Riemann zeta function, but he was proving all sorts of things involving the zeta function. And had he known that the Riemann hypothesis, had he known about the Riemann hypothesis, he would have changed what he predicted a little bit. So, yeah, so a lot of his mistakes, what underlied those mistakes was something that was an incredibly deep issue in mathematics, and when one studied that mistake, one would uncover something really incredible. So yeah, I think some of his mistakes were just absolutely telling. Yeah.
Okay, a question has been flashed by Manjesha. I'm a mathematics teacher. During this pandemic, how can we motivate students for learning?
Yeah, all us teachers are struggling with this question. Very good question. One has to, what I've found is that one just has to do things that one doesn't normally do in the classroom. Just do really out-of-the-box things, be creative, and teach things that you wouldn't normally teach in the classroom. This is a time to just forget a little bit about the curriculum and just do fun things. Keeping students' attention online is tough, and so the idea is just to have fun and do more unusual things that would normally happen in the classroom. At least that's worked for me.
Yeah. There's a question from Bandhan Goya. What if Hardy encouraged formulas more than proofs? If Hardy had encouraged, yeah, I think the question is clear.
Yeah, I spoke about that a little bit earlier. I think in hindsight, I mean, if we knew that Ramanujan was going to not be around after the age of 32, I think certainly, I think we all agree that it would have been better to let him go and produce his formulas, and mathematicians could spend the time to understand them afterwards, instead of having slowed him down with proofs. I think we can all agree on that. Although, when Hardy did encourage Ramanujan to come up with proofs, even though he was slowed down, he did come up with some incredible proof techniques. It's not that Ramanujan was not good at proofs. It's just that he was much more excited to move forward and produce more formulas. But the circle method is a great example. If Hardy hadn't pushed Ramanujan to come up with proofs, maybe we would not have had the circle method as we do today, which has now been used to solve so many other problems. So it's a really hard question. I think the correct answer is that Hardy should have made sure, this is something that many people fault Hardy for. He should have made sure that Ramanujan was eating well, that he had warm clothes, and that so that he could have survived beyond the age of 32. And then he could have done the proofs and the formulas, so it would have been plenty of time for both. That's really the ideal solution here.
Okay, here is a question from Mallikarjuna Reddy. He says, I'm a school maths teacher. I really want students to get inspired and by Ramanujan. How do I put forth, how do I tell students about Ramanujan's mathematics? I guess because it's inaccessible.
Right. Well, I did give you three examples today. I think two of those examples, the first two gems that I pointed out, first about partitions. Children can start to play with partitions very early. It's so elementary. How many ways can you take a number and break it up into parts? And I didn't get to tell you all the amazing things that, all the amazing identities that partitions satisfy, but they're all very, they're very elementary. You can study partitioning a number into odd parts, into distinct parts, and you find that and then you find various identities among these things. And then you can play around with how fast it's growing, and then you can show Ramanujan's formula for how fast it's growing. You can actually plug in numbers into the formula and get very good approximations to how many partitions a number actually has. So yeah, playing around with partitions, I think, is a really fun way to get into Ramanujan's mathematics. And then, of course, the taxicab number, the story about 1729, always inspires. It really shows that every number is special, every number has special properties, and then let the kids loose and find their own special properties of various numbers. You know, what's the smallest number after 1 that's both a triangular number and a square number? Questions like that. You can really appreciate the spirit of Ramanujan by becoming personal friends with individual numbers and seeing what properties they have. So these, I think, are two ways that you can really get into Ramanujan's mathematics and the way he thought about mathematics.
Okay. So there is a question by Jagadisha Tanusha. Did he work in any other areas, presumably other than, number theory, perhaps? Yeah.
He mostly worked in number theory and analysis, I would say. But he loved problems of all kinds. There are lots of stories of he and Mahalanobis discussing all sorts of areas. And of course, the things that he worked on, they look on the surface as number theory, but of course they've been used in physics and analysis. So they've gone beyond the areas that superficially it looks like he was working in. But of course, his notebooks were mainly about infinite series, about number theory, about analysis.
Yeah. I think we're almost running out of time. Before we conclude, I would like to raise this question from Abhinav Das, who's asking, why should not let research be pure and not bounded with borders? Why should a country take any credit for research? The research is all done for mankind. Why is credit necessary? He's saying, why should there be any national credit to mathematical research?
Yeah, this is also a tough question. It has often been the Indian attitude that, we do research for mankind and credit doesn't matter. But as a consequence of that, so many things are named after European mathematicians that were originally done by Indian mathematicians. A lot of things have been patented abroad when they could have been patented in India. So why does credit matter? Well, if everyone was only doing it for mankind, that would be one thing. But credit is, we live in capitalist countries where credit is a motivation, right? To work harder. And credit is also a way of ensuring that funding goes to the right places, right? If people are doing good work, if they're getting the credit for it, then they get to do more good work. So there's sort of practical reasons for why credit is important. But in the idealistic world, I do understand what you're saying. We should be doing, our individual motivations really should be that we do work for mankind, we want to better the world. But from a practical point of view, for ensuring that funding goes to the right places, so that children are inspired by people in their own country, they can get mentors who they know are doing good work so that they can learn from the best. For that purpose, for practical reasons, credit is important sometimes.
Okay, I've been told that should be one more is appeared there. Shubha Desikan, thank you for that absorbing lecture. Can you name one or two other works by other mathematicians that you have come across in your work that compelled you with the magical quality of Ramanujan's work?
Oh, there's so many. Oh, nice to see you, Shubha. You know her. Yes, many mathematicians, of course. Conway, who passed away recently due to COVID, actually, so this one of our tragedies during this pandemic. Conway's works have always inspired me with that magical quality, the way he came up with serial numbers, the way he came up with the 15 theorem that I mentioned earlier, his notation for symmetries, just these incredible discoveries, the way he thought about quadratic forms, the way he thought about lattices, very, very original. So he's another such magical mathematician that shows such incredible creativity and thinking out of the box. That was also very inspirational for me. Wiles, my advisor, was also an incredibly creative mathematician in a different way, just incredible depth. Barry Mazer. These are people in my field recently who did incredible things. When I read Gauss, Gauss also had just incredible ways of thinking that are just inspiring, so creative. So again, everybody has their own favorites. I'm just mentioning the ones that really seemed felt magical to me, just incredibly creative. And maybe if I'm allowed to go earlier than Ramanujan and Gauss, I would say when I was growing up reading Brahmagupta, that was one of the most creative works I've ever seen. Kinds of ideas in there that were back in the year 600. That's also something that I saw a magical quality in that it just blows your mind and inspires you. I wish Brahmagupta was taught more in schools as well. So anyway, these are some of the mathematicians that had those magical qualities that also inspired me. But Ramanujan, I have to say, was different than all of them in a way that when you read most mathematicians, you think, oh, I wish I could have thought of that. But with Ramanujan, when you read it, you don't ask that. You normally ask, how could anyone have thought of that? He had these leaps of faith that were not based in an education that would warrant being able to write something like that. And you would never ask, how could I have thought of that? You would think, how could anyone in the world ever have thought of that? And that happens more with Ramanujan than I've seen in any other mathematician, for sure.
Okay, I think the very last question now, because I'm told to take at least one more.
Sure.
This is from Professor Manish Jain. He's asking, what is the role of recreational mathematics and its relation with Ramanujan?
My view is that all mathematics is recreational. And, why did Ramanujan do what he was doing? I mean, even though his work is being applied all over the place, he was doing it because, as Hardy said in that clip earlier, just for the form, the artistry of it. And that's why people do recreational mathematics. It's incredibly artistic, it's creative. But if you approach all of mathematics like recreational mathematics, you'll see that mathematics really is artistic. You can pursue it for its form, and it's recreational. Of course, we also do it because it has practical applications in the world. But if you just look at the mathematics itself, mathematics is really an incredible subject. It allows you to explain the world through things that are incredibly beautiful and simple. And the joy of discovering them is like the joy of playing music or making a painting. So from that point of view, all of mathematics is recreational. And there's a lot of evidence that Ramanujan really pursued it for that purpose. He could get interested in a question that looks like it has no applications, and he could get interested in questions that do have applications. But he was in it for the form, for the recreation. So yeah, I urge everyone to look for the beauty of mathematics. I wish it was taught that way in school. I understand in school that sometimes it's hard. You're forced to mug for exams rather than sit back and enjoy the form of it. But I hope that can transform in school as well, that we get to see that artistic and fun side of it. Because that's really what it is. And we shouldn't take that away from our students.
That's I think that note of enjoyment is the right note to conclude the Q&A session on. I sincerely apologize to many for more than 100 questions out there that we could not take, but we are really running out of time. And I thank Manjul for not only the great lecture, but also a very patiently addressing the questions. Thank you very much. Over to Dr.
I'm really honored to have been a part of this. Thank you so much for organizing this.
Thank you.
I really appreciate it. Namaskar to everyone. Hope to see everyone again.
I'll give it to Dr. Parashar to formally conclude the session.
Yeah.
I think you have to.
Sir, you have to unmute.
Well, thank you so much, Professor Manjul Bhargava. It was indeed a very engrossing, very entertaining, and very informative lecture. I mean, the comments that we have been reading while you were speaking, they are more than hundreds in number. It's a clear manifestation of how much all of us love to hear you and all that you've shared with us. Thank you so much again and again for having accepted our invitation on such a great day that we've all been trying to do so. And what a finale to this Ramanujan Yatra, the idea that was conceived by a great friend and a science communicator of par excellence, Dr. Venkateshwaran. And also, in this entire journey, I'm touched to thank Dr. Ramanujan for his support all throughout the way. He started this Ramanujam Yatra by delivering his first lecture in Tamil, and I'm told that that was a wonderful lecture. All throughout this yatra, we had number of subject matter experts who spoke on various aspects of Ramanujam in different languages and in English. From the entire team of the Ramanujam Yatra, I express my thanks to them, and also to a number of people who've behind the scenes worked very hard to ensure that this yatra is a success. So now the audience, the curious minds, set of questions, all sorts of people that came our way, and I'm sure we've gone a long way in achieving our outreach program, in making people understand that mathematics, you don't have to dread mathematics, you have to love it. And that's exactly what Professor Manjul Bhargava rightly said at the end. It's all about looking at it in a recreational way. So there are a number of people whom I would love to talk about, thank them, but the list is so long that if I start, we'll probably end up talking for an hour or so. So I'll probably forgive me for not taking your names, but I, from the core of my heart and from the entire team, would like to thank all of you for having being with us and making this entire Ramanujam Yatra from April 26th till today a great success. Thank you once again to everybody here in India. Great night, and people in the United States have a great day. It's a holiday time. Please stay safe. Please stay healthy and be positive. Take care. Bye
Happy
now.
National Mathematics Day to
And
everybody.
happy National Mathematics Day. And thank you so much, Professor Bhargava. It was a great way to end this and a great grand finale. We remain indebted to you for having accepted our invitation.
No, thank you so much.
Thank you
Appreciate it.
so much. Thank
Happy
you.
National Mathematics Day. Happy birthday to Ramanujan.
Happy birthday, Ramanujan. That's right. Thank you.
Thank you. Thanks, everyone.